Hello student, welcome to our third lesson. Under here we are going to look at capacitors and capacitance. Now, a capacitor is a device that is used for storing charges. Note that there is a difference between a capacitor and a cell. When we talk of a capacitor, we are saying that it stores charges, but when we talk of a dry cell that we are maybe familiar with because we use it at our homes, a dry cell is a transducer, or a battery is a transducer. In other words, it converts chemical energy into electrical energy. So the work of a cell is to convert electrical energy into, the chemical energy to electrical energy, but the work of a capacitor is to store the charges. Now, a capacitor consists of two metal plates that are separated by insulating material. And that insulating material, we call it a dielectric. So when we talk of a parallel plate capacitor, we are going to use this as the symbol. This is the symbol of parallel plate capacitor. But what we are saying is that it consists of insulating material in between two metal plates. So you have a metal plate and another metal plate, and then we have the dielectric. Then we have the terminals. These are the ones that are connecting or that are used to connect in a circuit. Now, a dielectric can either be plastic, air, or glass. Remember, these are insulating materials. Then we move to types of capacitors. Now, the type of capacitor depends on its use. And also, it also depends on the material that is being used as a dielectric. For example, you have a paper capacitor, which implies that the dielectric is paper. Electrolytic, which means that electrolyte is the one that is being used as a dielectric. And then we have a variable air capacitor. When we talk of variable air capacitor, then it implies that the dielectric is air. Remember, all these, paper, electrolyte, and air, they can be insulators. We are going to see how each of them is maybe, or it works, or how it is made. So we start with variable capacitor. Now, in this capacitor, remember we are talking of variable. When we talk of the word variable, it means that it is changing. It has a variable capacitance. Now, what happens is that the effective area of the plate is adjusted. You can vary the effective area. And by changing the area between the plates, then you also change the capacitance. We have an example here that is shown in this diagram. In this example, we have two sets of semicircular plates. It can either be plates of brass or aluminium, and in between them is separated by air. That is now we call it variable air capacitor. So one part is fixed, and the other one you can rotate, because one set is fixed and the other one is rotated by the knob. So if these ones are fixed and then these ones are variable, then it implies that when you vary this, or when you turn this, you will change the effective area of the plates, and by so doing, you change the capacitance. Now, this type of capacitor is useful in tuning the radio circuits. Then number two, we have the paper capacitor. Again here, when we are dealing with paper capacitor, it implies that you can still use other types of dielectric. You can use the plastic, you can use the ceramics, or you can use the mica as the dielectric. So what happened, or how can you make a paper capacitor? You have two strips of metal foil, and then you attach your dielectric. You can either wax them, you attach the paper dielectric, and then you roll, as shown in this diagram. You have the strips, then at this side you put the paper, and then you roll. Then at the end you fix short wires, and these wires must be fixed on the metal foil. Remember, metal foil is the one that is a conductor, but the dielectric is not. The dielectric is not a conductor. So you make sure that the wires, these short wires, are connected to the metal foil. And these capacitors, they are used in mains supply, or where we have high frequency circuit. Then we have number three, we have electrolytic capacitor. Now in this one, it is made by passing a direct current in between aluminium foils that are soaked in electrolyte. In our case here, we are having aluminum borate as our electrolyte. So when the current is passed, we will have aluminum oxide that is formed on the anode. And you find that this aluminum oxide that is formed will act as a dielectric. That is why we are calling it electrolytic, because we are using an electrolyte. Now the film is an insulator and therefore acts as a dielectric. So electrolytic capacitor has much higher capacitance than paper types. The positive terminal of the capacitor should always be connected to the positive side of the circuit. And as shown in this diagram, this is what we have in our laboratories. The longer part here is having the positive, or it represents the positive terminal, and the shorter one represents the negative terminal. So this is what we call the electrolytic capacitor. From there, we can move to charging a capacitor. Now, remember we've said that a capacitor stores charges, but where does it get these charges from? We have to put charges to it through a process that we call charging. And during charging, we have this kind of the circuit. We have the source of power that is giving us the charges. We have the milliammeter, we want to measure the current. We have the voltmeter, of course, we want to know the potential difference between the plates of the capacitor. And we have the variable resistance. This is the variable resistor. So this will help us to vary the amount of current that is passing. So how do you go about this? When we close the switch, we observe that the milliammeter reading decreases. It is decreasing, while voltmeter reading increases. In other words, this one is decreasing from the maximum value to 0, and this one is again increasing from minimum value to maximum. So what is happening? We move to explanation. Now, if you look at this part, we have the negative charges here, because this is the negative terminal, and we have the positive charges on this side. So this negative is connected to plate B, which we are also calling it negative plate, and this other one is connected to the positive terminal, that is to our plate A, which is positive. So when the switch is closed, the electrons or the negative charges will flow from the negative terminal here to our plate B. So we shall have the charges flowing like this. At the same time, you will find that because there were some negative charges in here, at the same time you will find that the negative charges will flow to the positive terminal of the battery. So it means that the charges are flowing like this, from A to the battery, then to B. By so doing, you'll find that there will be equal positive and negative charges on the plate, because the electrons are coming here and the electrons are being removed here. So at the end, you'll have equal number of negative and equal number of positives on these two plates. So at the other time, when they are equal, remember now we have equal amount of charges, then we say that that will oppose the flow of electrons, because there will be no potential difference, because now they are having the same charges, and therefore that point the capacitor will be fully charged. So the charging current, this one, will drop from maximum to 0. That is when the capacitor is fully charged. The potential difference across the capacitor again will increase from minimum to maximum, and it will get its value. If this is 3 volts and this one drops to 0, that is the current drops to 0, then you will find that the voltage across the capacitor will also be 3 volts, meaning that the capacitor is fully charged. From there, we have the graphs. We have a graph of IT. When we talk of IT, we are referring to the charges, because we know that I multiplied by T will give you the amount of charge. Against time T will be like this. This shows that the graph shows that the charge increases with time and becomes maximum when the capacitor is fully charged. So as you can see, As you continue charging, you'll find that now the charges increases until it gets to its maximum when it is fully charged. Then a graph of voltage against time is as shown. So the potential difference also increases with the time, which implies that as charge increases, the potential difference between the plates also increases. And when charging, the current reduces to zero. When the charging current reduces to zero, the potential difference between the plates will be seen to be the same as the battery voltage. I've told you earlier that if it is 3 volts and the current is 0, then you find that the voltage between or across the terminals of a capacitor will also be 3 volts. From there, we go to the graph of current against time when charging. We have mentioned that the charging current drops from maximum to 0. And now the graph will be like this. This shows that the current is reducing until a time when it is 0. And at the same time, the voltage is increasing. So that is the graph of current against time. In other words, we are saying that the charging current drops to 0 when the capacitor is fully charged. From there, we can move to discharging a charged capacitor. Now, the circuit that we are going to use is this one. As you can see, there is no source of battery, or there is no source of power. There is no battery. We have just connected the capacitor with milliammeter and a resistor. And of course, we have the switch. So our observation, it is observed that milliammeter reading decreases from maximum value to minimum. But in here, remember, even during the charging, there was a decrease between maximum to minimum. But what we're supposed to note here is that the ammeter points in the opposite direction. Although it is reducing from maximum to minimum, the direction of current is opposite to that during charging. So then let us look at what is happening. Now, during discharging, the charges flows in the opposite direction. Remember, in our case, the charges were flowing from A, it was moving like this one, from A to B. But in here, during discharging, the charges are flowing from B, right? They are moving from B here, moving like that. So they are moving in the opposite direction as that of charging. And they will move until positive charges on A are neutralized. Remember, if the electrons are moving like this, they will come and neutralize the positive charges that are here. Maybe what you're supposed to notice is that when we connect in a circuit, what flows are the electrons. They are negatively charged. They are the ones that are free to move. So the electrons are moving, and when they come to the positive plate A, they neutralize, and they will continue until the charge on A is fully neutralized. And when all of the charges are neutralized, then the capacitor is said to be discharged and the charges between the plates will be 0. So the potential across the capacitor will practically diminish to 0. Remember now, as you connect the voltmeter here and you are discharging, the potential difference will decrease from maximum to 0. A graph of current against time during discharging, we have it here. As you can see, the current, yes, is decreasing from maximum to minimum, but it is in the opposite direction. That is what is happening. It is in the opposite direction. That is what we have this as our graph. The graph of voltage against time when discharging is as follows. We have seen that the potential difference across the capacitor practically diminishes to 0. So this is the voltage, it decreases. And it is decreasing because now the charges are neutralized. And when there are no charges between A and B, then there will be 0 potential difference between the plates. So from there we have the assignment. Again, the assignment is testing what we have just covered. So make sure that you practice a lot, and let us meet in our next lesson.